Section 1.5, absolute value equations and inequalities. This is the definition for absolute value. We have defined this on previous sections, but we just want to repeat it here. We know the absolute value of a real number is its distance from 0 on a number line. And we know that its symbol is the two parallel lines, and it is pronounced the absolute value of a -3, and we know the distance from 0 is 3. Here's the algebraic definition for absolute value. If x is greater than or equal to 0, then the absolute value of x equals x. If x is less than 0, that means x has to be a negative number. Then the absolute value of a negative number is a negative x. But recall, x is already negative, so it's basically implying the opposite. When we actually solve equations, we are given 3m minus 6 equals 12. But if we realize what 3m minus 6 can be, this expression can be either equal to 12, because if I simplify this and it is 12, the absolute value of 12 does equal 12. But I can also simplify 3m minus 6 to equal a -12, because the absolute value of a -12 is also 12. And that's why I have this explanation for 3m minus 6. This expression can equal 12 or -12, since the absolute value of 12 and the absolute value of a -12 gives the same solution of 12. Here's the procedure I'd like you to use to solve absolute value equations. Number 1, copy the problem. Number 2, use inverse operation to get the absolute value expression alone on one side of the equation. Number 3, now we need to set up two equations. This is how we do it. We set the expression inside the absolute value, so we take that outside the absolute value and set it equal to the solution. That will make our first equation. Then we want to set that expression equal to the negative or opposite value of the solution for our second equation. Then solve each equation as in previous sections. And then number 5, check the solution by substituting back into the equation. Let's look at an example. Here I copied the problem. Now I want to get the absolute value alone on one side, which it already is. So I need to create two equations. So I use the expression inside, 3m minus 6, and set it equal to the solution. Or I can also use that expression, 3m minus 6, and set it equal to the negative value of the solution, which is a -12. Recall, the absolute value of 12 is 12. The absolute value of a -12 is 12. I just need to find the value of m that makes this solution 12 and this solution a -12. So let's solve by adding 6 on both sides. 3m equals 18. Divide by 3. m is equal to 6. Or add 6 on both sides. 3m is equal to a -6. Divide by 3. m is equal to a -2. Now let's substitute back in to make sure they are true solutions. 6. 3 times 6 is 18. 18 minus 6 is 12. The absolute value of 12 is 12. That's true. -2. 3 times -2 is a -6. A -6 minus 6 is a -12. The absolute value of a -12 is 12. Both solutions are solutions of the original equation. Our next example, copy the problem. Also isolate our absolute value to one side. They both are. So let's set the expression 14 minus 2x equal to 8, or 14 minus 2x equals a -8. Solving the equations, subtract 14 on both sides. -2x is equal to a -6. Divide by a -2. X is equal to 3. Or subtract by 14 on both sides. -2x is equal to a -22. Divide by a -2. X is equal to 11. Let's substitute back in to check our solutions. -2 times 3 is a -6. 14 minus 6 is 8. The absolute value of 8 is 8. 11. -2 times 11 is a -22. A -22 minus 14 is going to give me a negative 8. The absolute value of a negative 8 is 8. Therefore, both solutions are true. Our next example, copy the problem. Then we want to isolate the absolute value on one side of the equation. Let's do that by subtracting 5 on both sides. That gives me a negative 3 times the absolute value of x plus 6 equals a negative 9. Divide by a negative 3. The absolute value of x plus 6 equals 3. Setting up two equations, let's pull out the expression. X plus 6 equals 3, or x plus 6 equals a negative 3. Solving each, subtract 6 on both sides. X equals a negative 3. Subtract 6 on both sides. X equals a negative 9. Let's substitute back in. Negative 3 plus 6 is 3. The absolute value of 3 is 3. 3 times a negative 3 is a negative 9. A negative 9 plus 5 is a negative 4. So this solution is true. Negative 9. A negative 9 plus 6 is negative 3. A negative 3, the absolute value of that is going to give me 3. 3 times a negative 3 is a negative 9, plus 5 is a negative 4. Therefore, both solutions are true. Our next problem, the absolute value of 2x minus 6 equals a negative 3. I could actually work through each problem by setting up the equations and then trying to substitute back in. But if we really take a look at the solution, here I'm taking the absolute value of 2x minus 6. Therefore, if I get any value here, whether it's negative or positive, the absolute value of that value is going to be a positive answer, and they need it to be negative. Therefore, no matter what value of x I substitute into this absolute value expression, I'll never be able to get a negative 3. Therefore, I have a null set or no solutions to this problem. An extraneous solution. An extraneous solution is a solution of an equation derived from an original equation, but it is not a solution of the original equation. This is why I always have you substitute back in at the end of the problem. At this point, all of our examples, each solution turned out to be true. But that is not true for all situations. Therefore, you always need to check to see which final solutions actually make the original solution true. Let's look at an example. I already have my absolute value isolated, so let's set up my two equations. 2x plus 5 equals, and when I have an expression on one side, I'm going to group that in parentheses, or 2x plus 5 equals 3x plus 4. Now, you can see why I put them in parentheses, because I need to make this one negative. Let's solve the equations. Here I have a positive 1, and if I distribute, I'll still end up with 3x plus 4. So I can just subtract 3x on both sides. That gives me a negative x plus 5 is equal to 4. Subtract 5 on both sides. Gives me a negative x equal to a negative 1. Divide by a negative 1. X equals 1. On the equation on the right, I need to simplify. 2x plus 5. Distribute with a negative 1. Negative times a positive 3x is a negative 3x. A negative 1 times a positive 4 is a negative 4. Solve the equation. Add 3x to both sides. That gives me 5x plus 5 is equal to a negative 4. Subtract 5 on both sides. That gives me 5x is equal to a negative 9. Divide by 5. X is equal to a negative 9/5. Now I have to substitute back in to see if all my solutions are true, none of them are true, or just one of them is true. Let's start with a 1. 2 times 1 is 2 plus 5 gives me the absolute value of 7, which is 7. Equals, and that's our question, 3 times 1 is 3 plus 4 is 7. That is a true expression, so this is a solution to the original problem. Substituting a negative 9/5, that's going to give me 2 times a negative 9/5 gives me 2 times a negative 9, which is a negative 18. over 5 plus 5. That's 5 over 1. And to make a common denominator of 5, I'll multiply the top and bottom by 5. That gives me 25 over 5. That gives me a negative 18 plus 25, which is 7 over 5, equals, and that's my question mark, 3 times a negative 9/5. 3 times a negative 9 is a negative 27 over 5 plus 4. 4 over 1, I need a common denominator, which is 5. Multiply the top and bottom by 5 gives me 4 times 5, which is 20 over 5. Negative 27 plus 20 gives me a negative 7 over 5. This is false. Therefore, x equaling a negative 9/5 is extraneous. In other words, it does solve this equation, but is not a solution to the original problem. So the only solution I have is 1. That's why you need to check all solutions to determine if they are all valid solutions to not only each separate equation, but the one that we really want, which is the original equation. So we have to determine the extraneous solutions.